Hi everyone. So welcome to this part two of this supplementary video. Um, what we will focus on in this video is coding up the solution that we derived in the first videos. Okay, so this is the feedback that we got in the mid-semester feedback, saying students would like to see some coding exercise. So just to recap, we discussed this solution of the problem of a cylinder rotating, and it's a unidirectional flow. So we got v theta e theta hat. And we said, v theta is only a function of r. We derived a differential equation. And with the boundary conditions of no slip and disturbance vanishes far away, we got the solutions omega capital R square by small r. Okay, so now this is essentially what we want to code up, and we want to be able to see what we get in our solution domain. Okay, in sort of visualizing this flow. So maybe let's start this process. So if you're not familiar with code, MATLAB, I will assume some basic knowledge of MATLAB. But if it is not there, don't worry. Hopefully, I'll still clarify some of the things that you need. Okay. So we have v theta equal to, so I'll just write it in terms of a comment. V theta is equal to omega into r square by small r e theta hat. Okay. So this is essentially what we want to code up in our system to visualize. So clearly the parameters that I really need this for are omega. So let's call that for initially 1. Then let's call r to be also 1. So this is the radius. This is the rotational speed of the cylinder. And I want to plot this, right? So how do I plot this? I have everything in terms of e theta, which is e theta hat, and then small r, which is r. So recall that. So these are my parameters, right? Parameters. So recall that r is equal to x square plus y square square root. Okay, and cos theta is equal to y by sine x by r, and sine of theta is equal to y by r. Okay, so we know this. Now I don't want to necessarily plot in terms of x and y. I want to plot in terms of r and theta. So let's first define some range of small r and range of theta. So range of r, so our domain is going from r to infinity, capital R to infinity. So I will go r times, and note this how I'm doing this. So I'll go from I'll say 0 to 1 comma 10. So what I'm doing here is I'm going from r to 10 times r. So to 10 times r. And what you're seeing here, this part here, this which I'm highlighting now, length space of 0, 1, 10 is dividing this 0 and 1 into 10 parts, so into 10 spacing. So 0, then with some equal spacing between 0 and 1. Let's do 11. So I can say 0, 0.1, 0.2, 0.3, 0.4 till 1. Okay, so these are 11 points from 0 to 1. And then I'm taking an exponent to the 10 to that number. So if 10 to the 0 is 1, so I get r. And then if I have 10 to the 1, that's 10. So I get 10 times r. So this should be more than sufficient for us to kind of see the decay of the velocity profile. Okay. Now theta always goes from 0 to 2 pi. So I will also say 0 to 2 pi length space as again equal spacing. And instead of calling this, 11, let's just call it n. And we'll just do n here, which is n is equal to 11. And these are my grid spacing. Okay, so grid points. This is my another parameter that I'm just using for plotting. Okay, so this is just, instead of manually writing, it's good to always parameterize it. Okay, so from 0 to 2 pi. Okay, so this is essentially what we have done. Now there is a command. So this is r and theta. We have divided r and theta into 10 points. But when I'm creating a 2D plot, I need sort of a mesh. A mesh means like I need to divide that up into boxes. So that's called a mesh grid command. If you're not familiar with it, don't worry, it's not that important. And this is just a mesh grid command to kind of create a mesh. So this allows division in 2D space. So that's basically RR and theta theta. Okay. So this is what I have for now. I've divided this. I will use this to create. This is essentially, it gives me coordinates for each point in terms of R and theta. I was just here dividing in one dimension, but this allows me to create two-dimensional spots. Okay. So I'll be created it in X and Y, and when I also have E theta hat. Okay. So we'll discuss this a little bit. So one thing is, now if I want to plot it in terms of X and Y, because that's how MATLAB will plot it, I can say, we know that this is RR into cos theta theta. So I'm doing an element wise multiplication theta theta. And then YY is RR into sine of theta theta. Okay. So this is essentially XX and YY, which is for just for plotting. So create Cartesian grid for plotting. Now my X component of the velocity. So now that is the part which I want to emphasize. Maybe let's go up and comment here also. E theta hat, and this is something we have discussed before, is minus sine theta I hat plus cos theta j hat. Okay, so this is what I will use to do the calculations. So now my u, which is the x component of the velocity. So this is x component of velocity, is omega r square. So omega into r square by small into r square by small r, right? So small rr, which is rr, right? Into minus sine theta, because this is minus sine theta for the I hat part. So I'll just do a minus here. And then I'll just for simplicity, I'll do sine of theta theta. And of theta theta by r. Okay, so this is essentially what I get for u. My v is same thing, but plus and cos theta instead of minus. I have plus into cos of theta theta. Okay, because the j hat is plus of cos theta. Okay, and if you're getting confused of between this theta theta and r and rr and theta theta, is basically the RR and theta theta are my each point, because I want to plot at each point. That's why I do this. I may recommend, just if it's not clear, I will recommend looking at the mesh grid function in MATLAB and playing around with it to just get a little bit of that sense. Okay, so this is my two results, and if everything is correct, so let's plot it. So to plot, we should say quiver xxyy q comma v. And just let's make line width to be 2, and then color to be maybe, let's say, K, I think should be fine, which is black color, or you can do blue if you would like. And then we should also want to maybe plot the cylinder itself. So we can say, hold on, there is a command called patch, I believe, in MATLAB, which and this is just to make the plot look a little bit better. And I don't know if it accepts colors or not. Let me check. I think it accepts the command color. We can check if there's an error, we can modify this. I'm just making some like to make it look good, and then just to make it look good, width. Let's make the line width everywhere 2. Font size to be 40. Pick label interpreter to be LaTeX. So this is just to make it look like a little bit nicer, adding a font size, some line width. And let's see if this works. Maybe there's an error, so let's see if this works. Seems to be running, and we get something here, but it's a little bit, maybe a bit too few points, and then too many points initially. So let's maybe zoom in. Yeah, I think it's a little bit too sparse, as you can see towards the end, and then too busy in the center. So we can kind of make it look a little bit better. So let's give me 1 second. I will just see if there is an error message in the MATLAB main window. Yeah, so there is no command as patch. So let's go and look up at the patch function MATLAB. So patch function is so sees the color. So hopefully we don't have to say color, I guess. Okay, so we just can just say here this. So I believe it should take it. Let's see. Yeah, so this looks, it has done something. Let's see, there's an error. So it says add a small error here. So it's line width. And then let's do it again. And by the way, there is a command called access equal. It just makes it look nicer to the command. Yeah, so this looks much better now, but still it is a bit sparse. So and you can see here we are getting these lines here, but they are maybe a bit too sort of sparse. So let's maybe improve this a bit. And I should note we can improve the n to be 21. And then maybe we should not go as much as until the 10 times the radius. We can just go 0.5 times the radius. Let's see how this looks. So somewhat better. You can see there's some nice plots coming in here. So you can see a circle. At the first, you can see it's all tangential. So it's kind of rotating in a circle, but it is decreasing as we are going along the radius, which makes sense because the disturbance is decreasing. And it definitely looks better, but I think maybe if we make it in more in sort of the theta dimensions, it will look nicer. Maybe we don't need more in radial, but more in theta to make it look a bit prettier. So how about we make it twice in the theta dimension, 2 times n in theta, and then let's see how this looks. Yeah, this looks better, I would say, definitely. And so you can see the velocity vector plots going around. Okay, so hopefully this kind of gave you an idea of how the velocity, when it moves, it can disturb. By the way, we can try to change a few things here and there. So this is for a radius equal to 1 and omega equal to 1. So what if I make omega to be 5, right? So if I make omega to 5, I should expect all the lines to become bigger. And I think it scales, and so this might be a little bit unrepresentative. So what quiver does, it scales by the maximum size. So it may not, but if you like kind of look at the value of u and v, this will be different. So this is like 0.2 and minus 2.6. So it'll be 5 and smaller if you look at the exact value. So that might just be the visualization effect, but you can scale the quiver command by that absolute scale if you would like. Here, yeah, so basically that's just wanted to give an idea of how to plot. We'll share this code with you. You can play around with it. And if you learned something new and want to share with us, feel free to do that. All right, hope this video was helpful, and I look forward to seeing you in the lecture.